So yeah, we'll be talking about fabrication-aware inverse design, which I put the inverse part in parentheses because I think it's kind of the same thing, really. So first of all, the outline of the talk today, or well, it's not really the outline of the talk, but more of sort of to get you to give you an impression of what we're trying to do today and what we're not trying to do, right? So one thing that I hope you'll get out of this seminar is if you are a PIC designer, that you'll learn a bit more about adjoint methods and how you can incorporate them into like a general design workflow. And on the other side, of course, I think if you're already familiar with inverse design and adjoint methods, you might not be as familiar with PIC design, and hopefully you'll gain something from that too. Because in my experience, there is surprisingly little overlap between the people that do inverse design and the people that do PIC design, which is somewhat strange, and hopefully this will be something for everyone. And this will be a very demo-heavy seminar, hopefully. So it'll be quite hands-on, and I think the examples that I'm going to show are hopefully things that will generalize to workflows that you may or may not be using already, and that might be useful to you. Non-goals of this seminar will be, we won't be talking about adjoint theory very much. We won't be doing a deep dive on the math there. We have great seminars that were already on our website on that, and there's also good literature on that. So if you're curious about that, I think there are plenty of resources. We'll just gloss over the sort of main ideas there. We're also not going to beat any performance records with the devices that we are going to be designing. So let that be said, right? So this is most of the things we are showing are kind of condensed examples to give you an idea of the general workflow and not really, yeah, we won't be pushing the limits of anything today. We're also not going to break physics. So that's, I think, another thing that is sometimes a sort of unspoken expectation of inverse design is that it's sort of a magic button that gives you awesome devices. It can be, but you'll see that, of course, you're always constrained by physics, and generally there is a trade-off. Great. So let's get started. The general framework for just design in general is kind of what I'll present here. It's this kind of three-step process, right? You have some parameterization that defines your geometry, your layout, the device that you want to simulate. You simulate that, and then you have some notion of whether that device does what you want or not, which you then encode via some objective function. And this pure forward simulation process is not, I mean, it can be useful, but generally it's not what you're looking for when you're doing design. When you're doing design, you're basically always doing inverse design. You're always asking the question, well, how can I tweak my parameterization such that I can improve whatever objective I'm going for? So this is just very, very general. This is also the reason why I don't really like this differentiation between design and inverse design, because to me, design is always inherently inverse design. Yeah. So the technology that enables a lot of the things that I'm going to be talking about today is this concept of a differentiable simulator. So Tidy3D is at its core is what we built is this differentiable simulation engine for FDTD, right? For electromagnetic, for solving Maxwell's equations. And the way that works is we try to make this differentiation as seamless as possible, and we leverage the same techniques that the machine learning frameworks do, which is you can basically just write Python code. Here is, for example, an objective function, and you as input. So if you remember this parameterization simulation objective picture, as input you have some parameters that define your device. You make your simulation based on that. You run that simulation, get some data out of it, and then you pull out whatever data is relevant for your objective. So you have this hypothetical here post-processing function, and that whole thing tells you then how good or bad your device is, right? It's in condensed into a single number. And automatic differentiation, what it does is under the hood, while you're doing this, it will create a computational graph and remember all the operations that you performed. And we did all the hard work. So we told this framework how to derive gradients with respect to such functions, such definitions. And then all you have to do in Tidy3D is call a gradient function on your objective with respect, like at certain parameters. And what you get is the gradients out of that quite seamlessly. Right. What enables this to be efficient, of course, is so generally in a simulation you have many degrees of freedom. It could be the permittivity in your simulation region, right? And that can easily go into the thousands or millions even of parameters. So the method that we use to make this efficient is the adjoint method, which you probably have heard about. If not, just a very quick refresher. This is not theory. The idea behind the adjoint method is you perform a forward simulation, which is just you run your simulation and you get your monitor data. And then as a second step, you run one additional simulation, which is the adjoint simulation. The adjoint simulation will have basically the monitors and the sources flipped, right? So the monitors in the forward simulation become adjoint sources with a certain phase and a certain magnitude. You get adjoint fields out of that. You multiply the forward and adjoint fields together up to some constants, and then you have your gradients. That's it. So, and you get these gradients with respect to an arbitrary number of degrees of freedom. So that's what makes this method so efficient. So it doesn't really matter how many degrees of freedom you have in your setup. All you have to do is run 2 simulations, and you'll have those gradients analytically. And yeah, as I said before, if you're interested in the theory behind that, we have plenty of seminars that go over this. Please have a look. But in general, so this method it's quite math heavy, but we package it all into this autodiff framework. And this is quite a powerful method. And we have a very extensive example library showing all the sorts of things that you can do with such a differentiable simulation. So please check that out too. All right. So that was it. That's all the theory for today. As the next step, we'll kind of go into the meat of this seminar. And the idea here is that we are going to, from scratch, design a component and go through all the steps through which you might want to go through when designing a PIC device, all the way from initial concept to finally a design that you can actually then fab out, measure, and calibrate. And the example that we'll be looking at today will be a dual layer gradient coupler, because it's, on the one hand, quite a simple geometry, so it makes for a nice demo, but it's also quite a difficult thing to design by hand. There are many methods to do it. All of them are tricky, take a lot of time. So the goal will be to design a dual layer gradient coupler that couples light efficiently from some fiber, so illumination, in C-band, so 1.5 micron, into a nitride waveguide. So the green thing here, we'll have a nitride layer, a cladding, a silicon layer, which will also be patterned, and a substrate. So quite the simple simulation setup. And yeah, so there are many ways to produce an initial design for these grading couplers. You can do this analytically via coupled mode theory. Of course, this is up to some approximation. You can do a unit cell approach where you kind of you calculate the Bloch modes of the unit cells of that grading, you stitch them all together and get a field profile. You can do a low-dimensional optimization, right? So you can, of course, also just sweep over grading periods or do a sort of global search. That is only feasible if you parameterize that design in a kind of low-dimensional way, meaning like a uniform grading, for example. And of course, you could also come up with an initial design using topology optimization. Today, we'll do this via a low-dimensional optimization, simply because it's easy. That's basically the idea. So I personally am not a good grading coupler designer. If you put me onto that task and I have to do it via like an analytical approach, I'll probably not do a very good job. But a low-dimensional optimization is something that is quite simple to set up and do. And that'll be our first demo. All right, so let's get into that. Okay, so yeah, we'll jump straight into code. I prepared a couple of notebooks, but the very first thing that we need to do is simply define a couple of variables that we will then use throughout all the other demos that we are gonna be looking at today. So that's just some general simulation stuff that we won't care about. We need to define our materials. So we'll have 3 materials here only. We have a box so the buried oxide that'll also act as our cladding, silicon, and nitride. Those will be our 3 materials. We define a Tidy3D medium based on those. So this will also be non-dispersive. We'll define the number of grading elements in our grading. So we'll have 15 elements in each layer. That is a realistic number. You can probably get higher performance if you add more, but this will work fine for our purposes. We'll also generally have to take care of a minimum and maximum width and gap, because those will generally just be imposed by the fabrication. We took some somewhat arbitrary but still realistic numbers here. So we'll have a minimum width of the silicon layer of 100 nanometers, a gap in silicon of 200 nanometers, and in nitride, we'll have a slightly larger feature sizes. Technically, we don't need a maximum, but generally it doesn't make too much sense to make these grading elements too large, and we'll just constrain the search space to 1 micron. All right. We will also have an offset. So the first tooth of the first silicon tooth will be offset from the waveguide. That's our first gap in silicon. And in nitride, sorry, and the silicon layer essentially will also have something we call a first gap, but this essentially encodes the layer offset between the nitride and the silicon layers. All right. And there will also be, very importantly, a spacer between the silicon and the nitride, so they will be separated by some distance, and we'll pick 300 nanometers here. Pick a wavelength, pick a resolution, simulation runtime, and that's all the parameters that we're going to need for now. We also define a couple of utility functions. So we will define the degrees of freedom that we have in our simulations, or the parameterization will be the width, the individual width and the gaps of each grading element. But because it's a bit easier to work with if those are defined in terms of centers and sizes, we have a little function that converts between those 2 representations. But that is not that important, just know that it's there. We'll create a function that makes our grading structures. So this is the thing that actually creates the geometry. Our input parameters will be the width and the gaps of those 2 layers for each grading element. Then a couple of other parameters that we will find useful later to parameterize over. We convert width and gaps to centers and sizes, and then we simply create those structures. We'll create the substrate, we'll create the individual teeth. That is relatively straightforward. These are just boxes in our case here. We'll place 15 of those in a loop and append them to the structures in our simulation. Same thing we're going to do. We will add a nitride waveguide, and we'll add the silicon teeth and return those structures. So that's our function that sets up the grading elements. Right, like this. And then finally, we'll have a function that actually sets up the simulation, which is sort of a higher level function. So it contains the grading structures and a couple of simulation parameters, right? For example, the parameters for the Gaussian beam and a couple of other parameters. This is not too important. Of course, we are setting up our source here. We're setting up the mode monitor for the waveguide. We'll include an option to monitor the fields too. And then finally, we just set up that simulation, and that's what's being returned from that function. So that function takes in our parameterization, and it spits out a Tidy3D simulation. That's the whole purpose here. All right. And then we'll also define a little convenience to get the mode monitor power from our mode monitor from the simulation data. But that's also just know that it's there. We'll use it in the notebooks. All right, so that's the general setup out of the way. And we'll go straight to the simulation setup notebook. That'll be quite short because we did all the work already. We simply set up a simulation. Whoops. We plot that. So this is how our initial simulation is going to look like. I just picked some more or less arbitrary parameters for the initial width and gap of the silicon. I'm also doing it uniformly. So these we will have 15 elements, but they will all have the same width and the same gap. Right, so that's what that simulation looks like. Setup looks sane. We run that simulation and get horrible performance, obviously, but that's the whole point, right? So this is our starting point. So we have something that we have a working simulation setup, and now the next step will be to actually optimize that, right? So we can go straight to the next demo. This is where we started from. We're going to do a little Bayesian optimization over those uniform gratings. So we will have 5 degrees of freedom in that optimization, which are going to be the widths and the gaps of the silicon and nitride layers. So that's 4 parameters. And then we add one more, which will be the offset between the silicon and the nitride layers. So we will have 5 degrees of freedom. This is still manageable with Bayesian optimization. We will use the Bayesian optimization package in Python to do this. Import all our setup. All we need to do really is define an objective function for this Bayesian optimization, which will set up the simulation using that simulation maker function that we defined. Runs it and returns the power at our central wavelengths. Yeah, so I should mention this. We will be designing this grading coupler for just the central wavelength. You can also do broadband optimization, but for the purposes of these demos, we're going to look at the central wavelength. Okay, and that's it. So we'll need to define some bounds for the width and the gaps. That's simply the bounds that we defined earlier. And for the first gap in silicon, we'll let it move around by plus minus 200 nanometers. So for the layer offset. We will run this for 60 iterations with a warm-up of 15 random points. So there's kind of a rule of thumb in Bayesian optimization is that you should pick 2 to 3 times the number of your degrees of freedom as like an initial random search. So that's why I picked 15, kind of just in between. We have 5 degrees of freedom. We'll start with the simulation that we already defined, so those default parameters. So we'll seed with that and then go from there. We set up the optimizer in the Bayesian optimization, and we simply run it, right? We do an optimizer.maximize. That gives us our, and that's gonna just go for a while and optimize our grading. So, and these highlighted lines here, I think, are always the current best results. All right, we'll look at those results. We found something. We have best parameters, a certain width and depth. So these are our 5 degrees of freedom. And the best objective value for that optimization was 45% coupling. That's not horrible. All right. And this is the search, right? We'll just plot that progress of the Bayesian optimization. You can see that so the red line is always the current best, and that that looks quite decent. But of course, because it's a global search, it'll like spend some time exploring the space too. We'll plot that final simulation that we found. Looks like this. And the spectrum that we get out of that, we ran it, plotted, that's what it looks like. So this is our starting design. So we started with something that didn't work at all and ended up with a spectrum that at least is starting to look like a proper grading coupler, right? So going back to that optimization, to just recap that very quickly, we started out with a sort of really, really bad initial design and got to a grading coupler after this global search, after Bayesian optimization, with a transmission of higher than 50%, which is respectable. It's not a horrible coupler. So the next question is, how can we push that further, right? So we can, so this is a grading coupler, but for sure it can be better. And one option, of course, is we could just let this Bayesian optimization run for a long time. But the more you get to an optimal design, the more there's a sort of diminishing returns story going on with Bayesian optimization. So once you have a decent starting point, that is really when you might want to look into locally refining that design. And locally always means gradients, right? So now we can actually do some gradient-based optimization. Oh, oopsie. So that'll be straight our next demo, right? So demo 2. So we'll take, the idea is very simple. We'll take that design that came out of the global search, out of the Bayesian optimization, and we'll plug that in, we'll take that as a starting point for doing adjoint optimization. So that'll be this notebook here. For adjoint optimization, I will just ignore the setup. That is quite, yeah. So what we need to do again is set up an objective function. It looks pretty much the same as the Bayesian one, because we'll have just something that creates a simulation, runs that simulation, gets the mode power, and then returns it as a scalar. We'll add a little minus sign here because we'll do gradient descent. So we'll want to, to increase the objective, we'll actually have to formulate it as a sort of as a loss, right? We could also flip the gradient signs, but this way it's a bit more, I find it a bit more intuitive. All right, we'll load the design that we found before. We'll run that adjoint optimization for 50 iterations. And now, very crucial, is we'll actually use a bit of a different parameterization. So you remember in the Bayesian optimization, because it's a global search, we were quite constrained in the number of degrees of freedom that we could pick in that optimization. So it was 5, and 5, in my experience, at least for these sorts of problems, really tends to be sort of the upper limit for efficient Bayesian optimization. You can push beyond that. It's not guaranteed to not work, but it won't work as well. In contrast, as I said, like in adjoint optimization, the numbers of degrees of freedom that you have in your optimization really don't matter, right? Because it's always two simulations to get your gradients with respect to those degrees of freedom. So what we'll do here is we will parameterize the width and the gaps of the silicon and the nitride layers for each grading element. So it won't be uniform anymore, but we will actually have degrees of freedom for each grading element, as well as the first gap in silicon, as well as the offset between the layers. So in total, that's going to be 15 times 2 times 2 plus 2, which is what? 62 degrees of freedom. And that's now far beyond what would be feasible with any sort of global search, because it's just a very high dimensional space. We'll add some bounds, and that's it. And you might remember from those first few slides is all it takes to get gradients for your objective function is you call the value in grad function on your objective. That gives you a new function that returns both the value of your objective function as well as the gradients with respect to its inputs. And that's it. We'll initialize our optimizer. We are going to use Atom here, just for simplicity. Also empirically, Atom actually works, I would say, unreasonably well for these sorts of problems. Of course, there are many other optimizers that you can use, all with different strengths and trade-offs. We'll use a learning rate of 1 to the minus 2, which, because of the parameterization that we chose, that's directly in micrometers, that corresponds to a maximum step size of 10 nanometers per iteration on each grading element. All right, we'll run this for our 50 iterations, get values and gradients, yeah, you'll see the optimization loop. We start out with something around here and end up somewhere around here. No need to read the values. We have a plot for that. So this is the optimization history. And you can see that we started out at around 52% coupling, and we optimized that thing up to around 58%, right? Which is a respectable increase. It's over 10%. You can also see that there's some wild oscillation initially in that optimization, which means that probably the learning rate we chose initially was too high, so which made the optimization somewhat unstable. So you can tune that, play around with it, make it more pretty. You can also see that it's not quite converged, so you might want to run it for longer, but for the purposes of the demo, this is a nice, basically free performance, right? We'll look at the spectrum before and after. This is what we get. So this is the grading coupler that we started out with. And after the adjoint refinement, we get a nice performance bump. All right. So this is what I just showed. This is a recap of that. So basically, doing adjoint refinement on some device or design that you already have is generally something that's very simple to do and really is, in my experience, free performance. All right. So this was all very conventional initial inverse design. But of course, this is not the end of the story, right? Because the real world gets quite messy. Many things can go wrong, right? So you can have, in fabrication, you can have all sorts of variations in things that can go wrong, right? Your layer thicknesses can vary. You can have sidewall angles or sidewall angles that can vary in your design. Your source can have a tilt that might not be what you're optimized for. Generally, alignment, kind of the same thing. You can have edge depth variations in your lithography layers. And there can also be lithographic bias, which means you can get like a global over or under edge in those layers. And there are many more. And of course, there are also rules that you have to abide by. So we already discussed minimum gap and minimum width. But in general, if you've ever done PIC design, you will know that there's something called DRC. There are rules that you have to abide by, and there are many of them, or can be. So the first thing that we need to do is kind of make sense of how these sorts of variations affect the design that we just made, right? To get an idea of what we actually need to what we need to do next. So that is where sensitivity analysis comes in. And the classic approach to that is essentially Monte Carlo, which means you're going to introduce random perturbations based on some assumed distribution of variability on each of the different parameters in your layer stack. You're going to do a bunch of simulations, you plot the spectrum and gain some insight via that. But what I want to show you is, of course, you can do that, but you can also use Adjoint to do sensitivity analysis. You can, from that, get importances of parameters, which means you will, because you have the gradients, right? They tell you which parameters in your stack actually have the most influence on the performance of that device. And you can even use Adjoint to very cheaply estimate the Monte Carlo distribution at a fraction of the cost, at a fraction of the number of simulations that you would need to do using Monte Carlo. So that'll be our next demo, right? All right, so we'll get into it. Sensitivity analysis. Again, couple of imports, same setup as before. We'll load our initial design. Well, our Adjoint optimized design. That's what we're going to load in. And now we need to do a bit of a special thing. So we'll make some assumptions here, of course. So this is a demo. This is not going to be full-scale commercial fabrication ready sensitivity analysis. So keep that in mind. The variations that we will look at for this double layer gradient coupler is the overlay date delta. And that means so what I mean by overlay is basically the misalignment between the two layers of the gradient coupler, because that is something that can happen in fab. We will look at the delta of the spacer, so the distance between the silicon and the nitride layers, and we will also look at the edge bias I have to make sure, in the silicon layer. So this is sort of a proof of concept. Of course, you can have a bias. So how does a bias in the width of your silicon grading teeth affect the performance of the device, right? We're only going to look at these three variations. In principle, you can do more, of course. You can put in all the parameters that you have in your setup. But for simplicity, we'll pick these. And also because these are actually the ones that we would intuitively expect to have a significant impact on the performance of a double layer gradient coupler, right? Because generally, for example, they will be quite sensitive to the distance between the layers, because that basically defines like an interferometric condition, right? Okay, so we'll return this. So what we end up with in this builder is a function where you can plug in these deltas for these three fabrication variabilities that we're going to assume and get spectra out of that. Okay, we'll also assume a distribution. So that is another bold assumption, but we'll make it for the purposes of the demo. Is we will assume that our fabrication variability follows a normal distribution in those three parameters, and we'll assume a standard deviation on the overlay of 25 nanometers, of the spacer thickness of 20 nanometers, and the edge bias in the silicon of 10 nanometers. So these are sort of realistic, but of course they will vary between fab processes and foundries. So the very first thing is we'll run in Monte Carlo. just draw 100 different samples from that distribution. We will run those simulations. We will include the nominal simulation and just run that. That'll be 101 simulations in total. The nice thing is we can use Tidy3D's one async, so we can run them all in parallel. But actually doesn't take that much longer than running a single simulation. But of course, we still pay for the credits of running the whole batch. Okay, so this is for plotting. We'll ignore that. And what we end up in the Monte Carlo simulation is this. Right here, we plot the nominal design, so the black curve, along with the mean, a percentile plot as well, and then in light gray, you can see the individual spectra of those 100 runs in the background. So you see there's quite a bit of variability, right? So a lot of designs perform worse, some actually go higher, but you have a variability in performance of like around 1.5 dB. All right. So this is just a table for plotting. We can kind of ignore that for now. This is the transmission at the center wavelength for all the samples that we drew. And we see that they're like it's kind of doesn't look quite like a Gaussian distribution, but we will pretend that it is. And of course, it's very much tilted towards designs that perform worse, which is not at all surprising because the nominal design was actually an optimized one. So it would be quite strange if there are the same number of designs that are better than worse than the optimized design. That would mean we didn't do a great job at optimization. And now, to contrast this, I want to show you what kind of insights we can gain from adjoint on this sort of sensitivity analysis. We load the nominal parameters again. We'll define an objective. You've seen this before. It's exactly the same thing as before. It's just the transmission at the center wavelength. And what we're going to do is we're not going to run 100 simulations, but instead we're going to do a single call to value and grad on the objective. Remember, the objective here is defined in terms of these biases, right? Yeah, so these are our parameters, not the individual grading teeth, right? We'll run that. That will run 2 simulations, forward and adjoint, and give us the transmission as well as the gradients with respect to those variabilities. And now there are quite a few cool things we can do once we have those gradients, right? So one thing, so we'll make another assumption here. So we've already assumed that our variables follow a Gaussian distribution. The next thing that we're going to assume is we're going to assume, because it's like gradients are local, right? We will assume that our device variability behaves approximately linearly, right? So that means we can do a sort of linear error propagation for these gradients. And once we know that, we can actually define for that Gaussian assumption, we can derive under those assumptions, we can derive a mean and a standard deviation with respect of the variabilities for using those gradients, right? What we also can derive from that is a contribution per variability parameter, how much it affects our objective function. Of course, the gradients already give you that in absolute terms, but we multiply by the standard deviation because that is essentially a weighting factor of how much these gradients matter for the individual variabilities. And we will normalize that by the total variability, just so that we have value between 0 and 1. All right, and if you look at that, you will see, so looking at the importance first, that actually we get kind of a funny plot. It looks like that the spacer, so the distance between the silicon and the nitride layer, completely dominates the response of that device, right? So actually, it's orders of magnitude larger than the variability that we expect to see from the width of the silicon elements or from the layer misalignment. All right. And what we can also do, so since we derived a distribution from the adjoint using those two simulations, what we also need to do is compare that to the Monte Carlo run, right? So here's again the distribution of the transmissions at the central frequency from the Monte Carlo run overlaid with the distribution that we derived from the adjoint. And the remarkable result here is that it actually matches quite well. So we made some assumptions on Gaussian distribution as well as linearity, but with those assumptions, they seem to hold decently well. We can actually get a similar distribution as at Monte Carlo from just a sensitivity analysis. And remember, the Monte Carlo took 100 simulations, and that the sensitivity analysis using adjoint only cost 2 simulations. Yeah. So that is what we saw. That's quite cool. And also so what that means in practice is, of course, Monte Carlo generally will still be the gold standard. If you want to make sure that you've captured your variations, you just have to do a lot of simulations over those. But as a sort of initial design exploration, you can get away with doing way fewer simulations, just running a single adjoint and looking at the distribution from that. And that can quite significantly speed up your design process. Okay, so the obvious question now is, once we have those sensitivities, how do we actually get to a design that isn't as sensitive to those fabrication variations? And the general approach here is that we can parameterize over a couple of these variabilities, get an objective value for each of those variations, and we sum over them in some way in our objective function, and then optimize over that. So that's a general flow. But of course, that can have, there are many, many, many decisions that you have to make when doing that, because there are many different things that you can sample, right? Do you want to sample all the fabrication corners? Do you want to sample all the variabilities? Do you want to, for example, sample also the indices of the materials? Those can also vary. Do you want to sample only very specific variations? There are many different ways to sample, right? You can do stochastic sampling. You can sample using quasi-Monte Carlo or assume some Gaussian distribution or pretty much anything else. You can also just pick very specific fabrication corners, right? And very often that makes a lot of sense to do. And what you can also do is, instead of sampling stochastically or picking specific corners, you can pick a worst case direction that again can be informed by your gradient and just include that in the optimization. And then there are also many ways to aggregate those results in the optimization, right? You can optimize over an average. It's a perfectly valid thing to do. You can optimize for the worst case. You can do a sort of weighted mean alternative. And that all depends at the end of the day on the specs that you're actually designing for, right? In our demo example, we had a very clear winner, so to say, in terms of which fabrication parameter actually plays the biggest role, and that seemed to be the spacer. So for the purposes of the next demo, what we're going to do is we're only going to look at that spacer and do an robust optimization that reduces the variability with respect to variations in that distance between the silicon and the nitrate layers. So we'll go straight to that. Again, same setup. And we'll define the objective. This one is going to look slightly different than the other ones, because now we're going to have multiple simulations within a single objective, right? Because we need to sort of average over them. So what that looks like is we are going to define a couple of simulations for each delta in the spacer that we're going to look at. And we're going to do this deterministically. So we'll take the nominal and then a spacer that goes that is like one standard deviation smaller and larger than the nominal. So overall, we will have 3 simulations. We will get the transmitted powers for each of those variations. And then we will calculate the mean and the standard deviation of those 3 values. And our objective function is going to be quite simple. We're going to maximize the mean and minimize the standard deviation. And then we included a sort of hyperparameter, which is the penalty on the standard deviation, which I put to 2. So we are saying that the standard deviation in what we're looking at is going to be twice as important as the mean. But of course, this is basically for demo purposes to show you that you can do kind of whatever. But yeah, it would work in any other sort of combination. So really, the design of this objective function is quite crucial because there you encode what you're actually going to want to be optimizing for, obviously. We'll run this robust optimization only for 20 iterations. So we're not going to use a lot of compute. Reason for that being, first of all, now we're actually running 3 simulations per iteration. So it's 3 times more expensive than the standard way. So 20 iterations will still translate to 60 plus the adjoint, so 120 simulations. And also, this is essentially just a little refinement, right, over our already optimized design. So 20 iterations probably is going to make sense. Again, we'll define the initial parameters and bounds. Again, the value in grad. This is always like a single line of code. And then we'll optimize for a couple of iterations. Again, history, that's what it looks like. And you can see that the objective increases nicely and smoothly. Seems to maybe even converge, who knows? But yeah, so we'll see what happens there. We will evaluate that final design and look at the spectrum before and after this robust optimization. And interestingly, so they are very, very similar, not much changed, but it looks like after this robust optimization step, the spectrum shifted, like it had a very slight redshift. That is probably due to the fact that it's slightly more robust when you go away from that peak, but we'll see that in a second, right? So here, this is just a recap. We looked at that, not that important. And now the really interesting part is we'll actually need to like analyze now whether or not this robust optimization worked, right? So we'll compare the robust and the non-robust designs. We'll have here a just again. So we'll do. I won't switch back to the demo notebooks for this. We're doing exactly the same sensitivity analysis that we did before, but now also for this robust design. These are the Monte Carlo runs. It's sort of hard to tell. You might see already by looking at that at the central wavelengths, the spread here is smaller. But of course, this is not like a super quantitative thing to look at. So instead, we're going to plot again the parameter importances for the baseline design and then for the robust design, because I think so this plot is actually quite interesting. The baseline design, again, you can see is completely dominated by the spacer thickness. But you can see that in the robust design, the relative importance of the spacer went down a little. I mean, it's still dominating. That's sort of just the physics of the problem. But you can see that relatively the layer offset and the grading and the edge bias gained a little bit of importance. And what that means, it tells us that it seems that our robust optimization decrease the importance of that the distance between those layers, which was exactly the goal of that, right? And it redistributed those sensitivities a bit. And the other thing that we need to look at is how the spread at the central wavelengths, because again, we were only looking at the central wavelength in these demos, compares between the baseline and the robust designs. And we have little box plots here, and what you can see is that there's a little trade-off, right? You lose around 1% roughly in transmission, in the mean transmission between those two designs. But importantly, the spread with respect to the layer the distance between those two layers was reduced by around 50%. So this is super important, because if you know that there will be significant variability in that layer in fab, then now on the right side, you will have a design that has significantly higher yield than the design here that was the baseline at very little loss of performance. Okay, so this brings us to the conclusion of the seminar. There will be, I hope, there are some takeaways for both PIC designers and adjoint and people familiar with adjoint. And most importantly for PIC designers, what I wanted to show you, and I hopefully was able to show you, that adjoint methods are quite practical tools, right? It's not some esoteric optimization technique, but you can actually make it really work for your design process and speed that up significantly. And you can, for example, for sensitivity analysis, you can very quickly get important insights without running hundreds of simulations. And these adjoint methods make hard problems like designing for specs for variabilities that are generally really, really hard to do and take weeks, literally weeks or months of design time. And it makes it quite feasible to do in a much shorter amount of time. So on that note, so this whole process from initial grading design to an optimized robust design, that whole thing took me around 2 days of work, right? So that is definitely faster than a couple of months, right? And for adjoint researchers, people that are familiar with adjoint, I hope that your takeaway is that PIC design in general offers quite interesting challenges, right? There are very rich objectives. You can get quite creative in how you formulate your objectives. There are many constraints on that fabrication process, and there's a great need actually for efficient methods to tackle that. And if you find good ways to do that, you can have a huge practical impact. And then obviously for everyone, like a more general takeaway is that adjoint methods are not only for inverse design. Adjoint methods are not only a thing that you can use for optimization, they're actually a useful tool that you can integrate at all stages of your design process, right? And this workflow that I showed here extends naturally to pretty much any other PIC device, as well as even beyond PIC. So all of the steps that I showed, you can apply in various ways to different photonic integrated circuit components. And sort of the underlying technology, what underpins this is really this differentiable stack. So the differentiable simulator, differentiable objectives, and all of that really enable this this workflow that drives you from initial nominal design to something that you can actually automate and drive your devices towards more fabrication-ready designs. All right, and with that, I will conclude my portion of so my monologue, and we can get to the Q&A. Just so you know, there is, in case you're interested, there's also a there is a bonus demo, but I think we'll stop here for now and just address a couple of questions and see where it goes. All right.